Okay, in this problem, it says a 10 amp current flows through the wire shown. There's the wire. What is the magnitude of the magnetic field due to a 0.5 millimeter segment of the wire? Yeah. 0.5 segment of the wire as measured at point A and point B. Okay. So now they don't give you the direction of the wire, current. If the current is flowing in this direction, what is the direction of the magnetic field at point A and B? If it's flowing to the right, so what you do is point your thumb in the direction of the current and your fingers point in the direction of the magnetic field. So the field would come out like so. Okay? And if the current were flowing in the opposite direction, the magnetic field would go into the plane. Okay? All right, so let's say the current is like that and the magnetic field is coming out of the plane. Okay? What we want is this segment produces that magnetic field, and we're finding the field at that point. This segment produces the magnetic field again in the same direction. All these segments produce fields in this direction. Okay? So you would just, if you wanted to find the field due to the entire wire, you would have to add up all these guys. And that was the integral. And that was the integral that you saw, this expression, mu naught 4 pi I ds cross r hat divided by r squared. Okay, we're not doing the integral. The field due to this segment is what we are finding. Okay, so dB, the field due to that segment is mu naught over 4 pi I ds cross r hat over r squared. All right. Okay, what is r hat? So r hat is a unit vector in this direction for point A. For point B, r hat would be a unit vector in this direction. Okay? So that would be r hat. R hat is a unit vector pointing in the direction of the point, okay, from the current element. All right, so now, so we already know the direction of the magnetic field. Now we just have to find the magnitude of the magnetic field. Okay, so there is ds cross r hat, ds, so this vector crossed with r hat would be a vector coming out of the field. And so this would be dB is mu naught 4 pi I dx over r squared. Okay. Okay, so all right, ds is if you want dx times I is the vector in this direction, and r hat is a vector in the j direction, cross j, it would be dx k I cross j. K is a unit vector in this direction, okay? And we already know that, so we are just finding the magnitude, so it's just I dx over r squared. Okay. All right. So this is that, and so now we can put in this these values. So dx is 0.5 millimeters. Okay, so mu naught is 4 pi times 10 to the minus 7 Tesla meter amp divided by 4 pi. The current is 10 amp. dx is 0.5 millimeters. A millimeter is 10 to the minus 3 meters. Yeah. And R is this distance, and that happens to be 3 centimeters. Yep. So 3 into 10 to the minus 2 meters squared. All right, so now we'll simplify this. This is 4 pi cancels. Let's take care of powers of 10. This is 10 minus 4. There's 10 minus 3, so that gives you 10 minus 1. That'll make this 10 minus 6. And the field will be in Tesla. And that is 10 times 0.5, which is 5 divided by 9. So 5/9 micro Tesla. So what is this? What did we find? The field strength, we know the direction of the field strength due to this little piece of wire at that point. We're going to do the same thing, find the field due to this piece of wire at this point. What do you think will be the answer compared to that? I'm sorry? It will be smaller because this distance is greater. The direction will be in the same direction, okay? So, but the strength of the field should be smaller, okay? So let's find that. So this is at point A and at point B, okay? Again, the expression is dB is mu naught 4 pi I ds cross r hat or r squared. Except that now, you see, for point B, here is ds, there is point B, r hat is in this direction, okay? So, ds cross r hat, the magnitude of this is dx, the magnitude of that, times the magnitude of this, which is 1, times sine theta. There is theta. Okay. And now sine theta is, so if you look at the diagram, that is 4 centimeters, that's 3 centimeters. So sine theta is, this is 4 centimeters, 3 centimeters, and that is 5. So sine theta is 3/5. So it's dx times 3/5. Okay. So dB is exactly the same, mu naught 4 pi I dx times 3/5 over r squared. Mu naught is 4 pi times 10 to the minus 7 Tesla meter amp divided by 4 pi. The current is 10 amps. Dx is half a millimeters, 0.5 into 10 minus 3 meters. What is R? R is 5 centimeters. Okay. And then dx 3/5. There was a 3/5 from here, from the sine theta. All right, so let's do this. And again, the 4 pi will cancel. Okay, powers of 10, this is 10 minus 4. You get a 10 minus 1 left. This gives you 10 minus 6. So 10 minus 6. And what is left is 10 times that is 5. 5 times 3/5 divided by 25. Okay, so this is 3/25 microtesla. The field over here was 5/9, so I mean this is almost half. Well, it's a little more than a half. This is much smaller at that point. Okay, so at this distance, the strength has decreased. Okay, the directions are the same. Okay. All right, now the field due to a small element here at this point would be the same as this. The field due to this element at that point would be the same as this. Okay, you got understand? All right. All right, coming back to this, okay, this is the ds element. What is the field due to this guy at this point? 0, because r hat would be a vector pointing, r hat would be pointing in the same direction, and ds cross r hat would be 0. So a current doesn't produce any field along the axial points. It doesn't produce any field there or there. Okay, and we saw that in the previous chapter. If you have a moving charge, it'll produce fields there, but B here is 0. Along the axis is 0. Okay, so just like that for currents as well. All right, so we're going to use that in this problem. All right, so here's a current. Now it's in the form of a loop. Okay, and you want to find the field at this point. Okay, so the accompanying figure shows a current loop consisting of 2 concentric circles, circular arcs, and 2 perpendicular radial lines. Determine the magnetic field at point P. Okay, this guy will not produce a field there. This guy will not produce a field there. This guy will produce a field there, and this guy will produce a field there. Now the currents are the same, but this guy is closer to that point. So this guy will produce a stronger field there than this guy. Okay. All right, let's figure out the direction of the field. Okay, so in what direction does this little element produce at that point? So what you do is you stick your thumb out in the direction, okay? And your fingers point in the direction of the magnetic field. So this little guy will produce a magnetic field coming out of the sheet. Okay? This little guy will produce a magnetic field into the sheet, except that this guy is weaker than that. So there will be a net field coming out. Okay? Do you guys understand that? Okay, so if you have a ds element like this, how do you figure out the direction of the field there? You point your thumb in the direction of the current, and your fingers point in the direction of the field. So this guy will produce a field that's coming out. Right? So similarly, this guy will produce a field like that. This guy will produce a field in the opposite direction. Except that this is weaker than that because that guy is further away from this point. Okay? All right, so we understand all of this. dB, the field due to a small element is mu naught 4 pi I ds cross r hat over r squared. Okay, let's concentrate on just this one element. Okay, so we're looking at this element ds. There is r hat. Okay, r hat is a unit vector, ds is dx. ds cross r is a vector coming out of the sheet. For this element also the vector is coming out of the sheet. For this element also the vector is coming out of the sheet. So for this entire thing, if you wanted to find the field due to this entire thing, you do an integral. Okay, so for arc A, B would be mu naught 4 pi integral I ds cross r hat r squared. Well, r is the radius A, and that's constant, a squared for all those elements. So that would, so B due to arc A would be mu naught 4 pi, I is constant, r is constant, and we already know the direction of this, it's coming out of the sheet, and this would be just dx, sum of all dx, sum of the lengths of those elements. Okay, and the sum of the length of the element is just this arc length. And what is the arc length? 2 pi r is the radius, entire radius. 2 pi r is the circumference, it's 1/4 of that. Okay. So what this is, mu naught, and that leaves a 2, 8 mu naught over 8 I over A. Okay, so what this is the field due to this arc, circular arc at that point. Essentially, we were able to do this integral because it was a symmetric situation. If you wanted to find the field of this guy at this point, you were out of luck. Okay, that would be very hard to do. You couldn't do this integral essentially. Okay, so now the field due to this guy at this point is that. The field due to this guy will be negative in the opposite direction. Okay, you guys understand? This guy is producing a field coming out of the sheet, and this guy is producing a field into the sheet. All right, so the net field, the total field is BA plus BB. So the total field is mu naught over 8I 1 over A minus 1 over B. And it's coming out of the sheet. A is smaller, and so there's a net field coming out of the sheet of the paper. See, we were able to obtain an expression like this only for a very symmetric point. You can't get an expression like this for a point over there or there, okay? So that's the field, okay? Okay, so this problem says, oops. So you want to find the magnetic field the magnitude of the magnetic field, 50 centimeters from a long thin wire is 8 microtesla. What is the current through the wire? So here's the current. So if you have a long straight wire, how are the fields? You point your thumb along the direction of the current, and the fields are concentric circles like that. And at a distance r, the field strength is given by mu naught by 4 pi I, or is it I over 2 pi a. Okay. Let me make sure of that. The factor. Yeah, 2 pi a. Okay. So they tell you that, or so since we've used R, we'll, okay, R is the distance, okay. So they tell you the field is 8 microtesla and the distance is 50 centimeters. So now we can solve for I, okay. I would be 2 pi R times B over mu naught. R is 0.5 meters, B is 8 microtesla, and mu naught is 4 pi times 10 to the minus 7 Tesla meter. Yeah. Okay, that's 2. Okay, let's take care of powers of 10. That's 10 minus 1. That comes to the top. That becomes 10 to the plus 1. So now that is 5 times 4. Yep. Amps. Okay, 20 amps. So that's a large current. From a 20 amp current, half a meter away, the field is 8 microtesla. Okay, and that's roughly about half the field strength of the Earth's magnetic field. So if you have a 20 amp current, half a meter away, that's about half the strength of the Earth's magnetic field. Or not half, not roughly a tenth. All right, so this problem says a long straight horizontal wire carries a left to right current of 20 amps. So here is a wire carrying a current of 20 amps. If the wire is placed in a uniform magnetic field of magnitude 4 times 10 to the minus 5 Tesla, this is the Earth's magnetic field roughly, that is directed vertically downward. So now the Earth's magnetic field would be downward, directed vertically downwards near the poles. Okay, so this is the external field, and this guy, okay, that is, what is the resultant magnitude of the magnetic field 20 centimeters above the wire, 20 centimeters below the wire? Okay, so there's the external field. Oh, we'll call it B naught actually. And this wire, okay, what does this guy do? He produces the magnetic field. And what is the direction of the magnetic field he produces? So at the top, it'll be coming out. At the bottom, it'll be going in. Okay, so this guy will produce a magnetic field going in and there like that. Okay. So, and this field, okay, what is that field going to be? At a distance r, B will be mu naught I over 2 pi r. Okay. So what we'll do is we'll just do it at the bottom. At the top, it'll be similar, except that in the opposite direction. Okay, now let's look at the side view. So side view. Okay, so the field due to the Earth, B naught is in this direction, and B is, and this is the direction of B, equal to mu naught I over 2 pi r. Okay, so what we're doing is we're looking at it from this angle. We're looking at, there the B naught is going down and B is going into the sheet, and that's how it's, you see it, looking at it from this angle. And this will be the total field. The total field will be that. Okay. So let's calculate B first. Okay. And then we can calculate this magnitude. Okay, so that'll be just using the Pythagorean theorem. Okay, so let's calculate this B. Oops. B is mu naught I over 2 pi A, 2 pi R. Mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. I, the current is what? 20 amps. 2 pi, and R, we are calculating the field how far away? 20 centimeters below. Okay. All right, so this will cancel. Again. That gives a 2. That makes it 200, and then we'll absorb 2 of them, so that's the 2 will cancel, so that makes it 100, and 10 to the minus 5. So this is 2 times 10 to the minus 5 Tesla. Okay, so again, what we have calculated is the field due to this current which goes in that direction, the magnitude 20 centimeters away is 2 times 10 to the minus 5 Tesla. This is 2 times 10 to the minus 5 Tesla, and this is 4 times 10 to the minus 5 Tesla. Okay? So again, this is B is 2 times 10 to the minus 5 Tesla, and B naught was 4 times 10 to the minus 5 Tesla. Okay. So the magnitude of the net field is 2 square plus 4 square times 10 to the minus 5 Tesla. Square root of 20, and square root of 20 is okay, that's the net field. All right, so let's look at the diagram. So this field goes in, there's the field. So the field due to the net field would be into the sheet like that, not perpendicular to the sheet, and this field is coming out down, and that will come out at an angle from the sheet. Okay. Okay, again, in this problem, the wire is producing a field, and here is the external Earth's magnetic field. So what this is showing you is, so if you're using a compass, if you use a compass near a current-carrying conductor, it won't point towards the Earth's magnetic field. it'll point at a field that is, instead of the compass pointing like this, it's pointing like that. Okay. All right, so this problem says two long straight wires are parallel and 10 centimeters apart. So okay, one carries a current of 2 amps and the other carries a current of 5 amps. If the two currents flow in in opposite directions, what is the magnitude and direction of the force per unit length? Okay. You saw that if the currents are in the same direction, they attract each other, and if they're in opposite direction, they'll repel each other. Okay. And you can figure this out easily. Okay, so if for this guy, you figure out the magnetic field produced by this guy there. So if this guy is, so the field produced by him there is V2 is in this direction, and the force he'll exert, so I cross B2 will be a force in that direction. Anyway, opposite currents repel each other, and the force per unit length is given by mu naught I1, I2 divided by 2 pi r, where r is the distance between them. Okay. So if the two currents, what is the magnitude and direction? So here is the magnitude. So if the currents flow in the same direction, that would be an attractive force. So force per unit length is mu naught 4 pi times 10 to the minus 7 Tesla meter amp. I1, I2, 5 amps times 2 amps. (10 centimeters, 0.1 meters). Okay, so that's 0.1, we'll kill that. That's 10 minus 6, and that's 10 times 2, 20. Okay, so 20 times 10 minus 6 Tesla. Oh, no, this is a force per unit length, Newton per meter. Okay, that's what it works out to. 20 micronewton per meter. And that's the force per unit length of the wire. So if the currents flow in the same direction, the force is attractive and has the same magnitude. And same magnitude. Okay. Maybe we'll solve a couple more problems. Okay, so here's a flat circular loop. It has n equal to 20 turns. I is 0.5 amps. And we want to find the magnetic field at the center of the loop. And again, we don't have an expression for any other points. Okay, so we have expression for the center of the loop or points on the axis. Okay, and what is the direction of this field at the center of the loop? So you point your fingers in the direction of the current, and your thumb points in the direction of the magnetic moment, which also points in the direction of the field. Okay? And the field is given by, okay, so here's the expression. There, okay. It's given by that. R is the radius, Z is the coordinate along the axial point. So for our case, Z is 0, okay? But I'm going to write this expression. So mu is NIR squared. Okay. So for us, Z is 0. So B will be mu naught NIR squared 2 over Z is 0, and R squared to the power 3/2 would be R cubed. So B is mu naught NI over 2R. So that's the field strength at the center of the loop. Okay, so now we can put in these values: 10 to the minus 7 Tesla meter amp. N is 20, and current is 0.5 amps divided by 2. The radius is 0.51 meters. Yeah? All right, let's take care of power. So 10, that's 10. Okay. Well, that'll make it 10 minus 6, 10. That makes it 5. So it's 20 pi into 10 minus 6 Tesla. B is 20 pi microtesla. And pi is 3.14, so roughly about 65 Tesla, 63 Tesla. Okay. 63 microtesla. Okay, so this problem says 2 flat circular coils, each with a radius r, and wound with n turns, are mounted along the same axis, so they are parallel a distance d apart. What is the magnetic field at the midpoint of the common axis if a current I flows in the same direction through each coil? Okay, so I'm just going to show you how to do this. Okay, so they're asking you the field at this point, I. Okay, so this will say this is loop 1, this is loop 2. Loop 1 will produce the field due to loop 1 will be B1 will be that. The field due to loop 2 will also be in the same direction. They'll add up. And this distance is D. So this distance is D by 2. Okay? So what you do is, in each of these expressions, mu naught NI R square divided by 2 R square plus Z square to the power 3/2. In each of those expressions, you just put Z equal to D by 2. Okay? And so the net field will be B1 plus B2, which will be 2 times, and So both those expression R is the same, Z is just D by 2. That's all. 2 times mu naught N I R square over 2 times R square plus D square by 4 to the power 3 halves. Okay? And that's what the field is. Okay, that's an easy one. All right, so we'll do this one. If a current of 2 amps, how many turns per centimeter must be wound on a solenoid in order to produce a magnetic field of 2 millitesla within it? So this is a straight up solenoid, and you want to produce a uniform magnetic field inside, and the magnetic field is given by mu naught N I, where N is the number of turns of wires around the solenoid per meter, okay? And the current is given to be that. How many turns per centimeter must be wound, okay? So N is equal to B over mu naught I, 2 into 10 to the minus 3 Tesla. Mu naught is 4 pi into 10 minus 7 Tesla meter amp. And I is 2 amps. So what we get is, okay, the 2 will cancel. You get 10 to the power 4 over 1 over 4 pi. And this is per meter. That's how many turns you have per meter. So this is 796 turns per meter, okay? And if you want to convert that to centimeters, 1 meter is 100 centimeters, so you divide this by 100. And so that is 7.96 turns per centimeter, okay? Or 8 turns per centimeters. A centimeter is that much, and you have 8 turns of wire in that centimeter. Yep. All right, I'll quickly do this problem because it's an Ampere's law problem. Here's what Ampere's law states. The line integral around a closed loop is equal to mu naught times the total current threading through that. All right, so this is a toroid, has 250 turns of wire and carries a current of 20 amps. Okay, so a toroid is a donut-shaped region, and this is wound with wires. So the current is coming out here and going in here. Current is coming out here, so it's wound like so, and current is coming out and going in like this. And it is producing a magnetic field, which are concentric, which are circular field lines. Okay, so the magnetic field for a given radius will be constant. Okay, so this line integral will go around this closed loop, and the line integral will be the line integral would be just b times 2 pi r. This is just b times 2 pi r. Okay, and if you go do the line integral in this sense, what this is the total current within this loop, and what is positive is current going into the sheet is positive. You point your fingers in the direction of the line integral and your thumb points in the direction. So these currents are positive, and these currents don't contribute because these currents are outside the loop. So it's only this. And how many of those guys are there? There's 250 turns, so 250 of those currents are pointing in. Okay? And so that's equal to mu naught times n times I. Okay? So b times 2 pi r mu naught and number of turns times the current in this loop. Well, what I'll do is I'll call this total. Okay. N times I. So B is mu naught N times I divided by 2 pi r. Okay, so what is this? The strength of the magnetic field. As R increases, the field is strongest on the inner walls of the toroid, and it's weakest on the outer walls of the toroid. Okay? Now, generally, the thickness of the toroid is small compared to the size of the entire toroid, and so it's essentially uniform. But you saw that, so for the tokamak, that's a fairly large volume. Okay, so it does, the strength of the field does decrease as you go out. Okay. All right, so now we'll calculate for various radii. They want you to calculate for various radii 8.1, 8.5, and 8.9 centimeters. We'll calculate it for this guy for 8.5 centimeters. Okay. So the magnetic field is mu naught 4 pi times 10 to the minus 7 Tesla meter amp. N is 250 and current is 20 amps, and 2 pi R is 8.5 centimeters. Okay. So that makes this 10 to the minus 5. That cancels, that's 2. Okay, so, and well, that's 10 to the minus 5 will absorb 2 from there, so that's 10 to the minus 3. Okay, so 10 to the minus 3 Tesla, 2 times 2.5 times 20 times divided by 8.5. Okay. So B is 11.8 10 to the minus 3 Tesla. 11.8 millitesla. So what we have found is, so in a toroid, which is roughly a feet wide, 1 foot wide, and if you pass a 20 amp current, the field inside is about 10 millitesla, which is about 100 times stronger than the Earth's magnetic field. The Earth's magnetic field is half a Gauss, which is 5 times 10 to the minus 5, so about 200 times stronger than the Earth's magnetic field. Okay, so you take a toroid that big, pass a 20 amp current. Yep. In those tokamaks, the fields are much, much stronger. All right, guys, so we'll stop